In this podcast, we're going to analyze algorithms beyond sorts and try and figure out basically how efficient they are using something we call Big O analysis. We're not trying to compute exactly how long something is going to take. We're just going to try and figure out whether it's going to happen relatively quickly, relatively slowly, long enough that you're going to be dead, or long enough that the entire universe is going to be dead by the time you're done. Close enough for horseshoes and hand grenades. To review quickly, we said that sequential search basically takes n tests to find an item in a list of n. We know that if we double the size of the list, it will in general double the time of our search. So we call that a linear algorithm. We talked about binary search, which was doable in log base 2 of n, so we call that a logarithmic algorithm. Our sequential sorts operated in time n squared, so you can guess we call that a quadratic algorithm. And the binary sorts, like the quick sort and the merge sort, operate in n log n time. Well, no one came up with a creative name for that, so we just call them n log n algorithms. And to clarify what we're talking about, when we talk about an algorithm that executes in that time, we say it executes in order n, or order n squared, or order n log n. It's not quite an order of magnitude like we learned in science, because that was based on powers of 10, but it tells us how bad the execution time might be. And we could also think of a very simple algorithm that operates in constant time, order 1, if you will, or order C, sometimes referred. And there's a good example of it. There is no n. It just executes in whatever time it takes, and it doesn't matter how many items it's dealing with. Now, it can also get worse than quadratic. In fact, it could be a polynomial of essentially any order. We call them order n to the x, or polynomial, or class P algorithms. Weather forecasting is a good example of that. You forecast the weather in a computer by breaking up the atmosphere into individual cubes, let's say 1 kilometer on a side, and take a look at the wind direction, temperatures, humidities, barometric pressures, and other things going on in that 1 kilometer cube. You then look at all the cubes next to it, and you figure out what's going to happen in those in the next, 10 minutes, based on what was happening in that internal cube. And then you do it again for the next cube, and the next cube, and the next cube. That's why it takes really big computers. One way to increase the accuracy of the forecast is to increase what we call the granularity. Cut the size of the cube that we use. If we cut the dimension of that cube in half to 1/2 kilometer, however, it doubles the granularity, perhaps doubles the accuracy, but it makes the processing go up by the cube of 2. So if we take something with n and it goes up by n cubed, you can see it's worse than quadratic. And you can come up with other examples like speech processing, where it tends to go up by a polynomial of, 25 or 30. It can get worse than that. We can go up exponentially. The example used is the king putting rice on squares of a checkerboard. And we all know by now that by the time he gets to the 64th square, he's going to be up to 2 to the 64th, which I think we concluded was somewhere around the number of stars in the known universe. It's a big number. But wait, it gets even worse. Factorial expands even further than that. We use factorial a lot in probability, and some of that has applications in very important algorithms. Probably the most important is what's known as the traveling salesman problem. If you have to hit all of those cities, what's the cheapest way to get there? Well, basically, the best way to figure it out is to take all the possible permutations starting in Boston and going to all those different other cities. That's n factorial. Here's another example. If you have 300 random numbers and you need to find all the sets of 3, Well, that's 300 choose 3, and we know that that's got some pretty nasty factorials in it as well. Here's another great example of a factorial algorithm. Who cares? Well, you do. Anything secured on the internet, or in a cell phone conversation through encryption, relies on the fact that this is a really difficult problem to solve. If somebody could figure out how to solve this problem really quickly, well, there's certain unmentionable agencies who would be very interested. If we look at graphically what's going on here, we see that the factorial and exponential algorithms and even the polynomial algorithms increase very, very quickly as the number of items you're dealing with tries to increase. We can summarize by saying if we take the universe of all the problems that we'd like to compute, we can break them up into several subgroups. Polynomial and more efficient algorithms are generally considered tractable. We can put them on a fast enough computer, and we can generally solve most of them in the time that makes sense. There are also algorithms that are worse than polynomial in the exponential or factorial area, where we consider them non-deterministic polynomials. We can solve them if we throw enough processors at them. You saw an example of this with some of the parallel sort algorithms. And there's an interesting subset of those where we've shown that although we haven't figured out a polynomial way to solve a particular problem yet, if we did find a way, we could solve a whole class of problems using a similar kind of polynomial technique, moving a whole bunch of things right now that take gobs and gobs and gobs of processors back into the realm of possibility. If you happen to solve any of those, contact the NSA. I'm sure they'd be very interested in your solutions. Or here's a paranoid thought. Maybe they've already solved them. Careful what you send over the internet.